All right, welcome everybody to 16.1, which is entitled Illumination. We're going to be talking about light today. What it is, why we call light light, the speed of light, different electromagnetic waves that are not light, the difference between the sun and the moon in terms of light, transmission of light, why some things can go through and others don't, how we start measuring light. We measure how bright surfaces are, how bright this lamp is, and then what's called the inverse square relationship. And then we'll finish off with a couple of example problems today. Example problem 1 and example problem 2 from 16-1 in your book. So let's get started. Light is the range of frequencies of electromagnetic waves that stimulate the retina of the eye. All that means is light because our eyes see it. Now I'd like you to watch this video with my friend Richard Feynman. He's one of my favorite physicists, and I'd like you to watch a 5-minute video where he explains what light is to the common layman. Light, the range of, these are wavelengths right here. 700 nanometers is blue. I'm sorry, I take that back. 400 nanometers is blue. 700 nanometers is red. And that these nanometers, they're talking about the spacing from wave to wave. Light's speed. We are going to use 3 times 10 to the 8th meters per second for all of our calculations. But the true speed of light is 299,792,458 meters per second. That is, and there's a really interesting story behind this, which is the topic of another whole lecture. But the speed of light will not change. As we get better and better and better at measurement, what does change is the meter. We have defined, the scientific community has defined the speed of light to be exactly 299,792,458.0 all the way out to infinity. As we get better at measuring, they make the meter itself will adapt to the speed of light. And we see it in equations as E equals m, the letter C. This letter C here is the speed of light. Now, you can see my background here. My background is what's called the Hubble Ultra Deep Field. And it's a picture that you can find if you just type in Ultra Deep Field. I went to Hubble's website, and it's really, really interesting. This is probably one of the most profound images ever taken in humanity. It's the Hubble Space Telescope went around the Earth 200 times, snapping 2 pictures every single time. So this is literally 400 pictures stacked together. And these, what turned out, are galaxies. Tens of thousands of galaxies are in this picture. Every single spot of light that you see as you scroll around is a complete galaxy made up of billions and billions of stars. You can learn more about it on Hubble's website. Very, very cool. The electromagnetic spectrum. The electromagnetic spectrum is all electromagnetic waves, and we only see a very small fraction of them. If you were to stretch this from LA, Los Angeles, to Washington, D.C., we would only see 1 inch of all the electromagnetic waves. These little things in front of our faces, these eyeballs that we have, see a very, very small piece of the huge scope of what is out there. There is stuff below what we can see, and we call that infrared. Just like there is sound below what we can hear, we call it infrasonic. There is stuff above what we can see. We call it ultraviolet. above violet, below red. And other things above what we can see, X-rays, gamma rays, things below what we can see, radar, FM, television, shortwave radio, AM radio, all of these things are below. Now these things over here are dangerous. You might notice X-rays, not good for you. UV rays, they give you sunburn. Gamma rays, you might not know what they are, but all of Earth hangs in the balance right now, hoping that we don't get bombarded by a gamma ray burst. They come from a dying star. And if we just happen to get hit by a gamma ray burst, it could irradiate all life on planet Earth in seconds. Oh, something else to just look at. As we get more and more energetic, the wavelengths get smaller and smaller. As we get less and less energetic, these things are all pretty harmless over here. FM, TV, short, those things are all in the room right now. They have a longer wavelength. On the order, well, it doesn't really, on the order like FM radio, a 1 meter long wave. AM radio, it's 10,000. It's 10 kilometers from peak to peak. The moon and the sun. The moon, when you look at the sky, it is reflecting light. The moon is reflecting. We call this an illuminated body. It is being illuminated by something else. What is it being illuminated by? It is being illuminated by the sun. This is giving off light. We call that a luminous body. Now, when light encounters a boundary, some of that light, some of it bounces off, some of it travels through. That transmitted part through it depends, like what the boundary is made of. Like if the boundary lets a lot of light through, we call that transparent. If the boundary lets a little bit of light through, we call that translucent. And if it lets no light through, we call that opaque. Now, sources of light. There are a few different terms we use when we're talking about light. The first two I want to talk about are luminous flux and luminous intensity. Luminous flux is the rate at which light is emitted from a source. Its units are lumens, and we see it in equations with the letter P. So if you look down here, you'll see this is P. This is in lumens. Down below, luminous intensity. That's how the luminous flux that falls on a square meter of a sphere that is 1 meter in radius. Its units are candela. Now, let me show you exactly what I mean by that. So this is not found anywhere. Illuminance, the letter E, that's this guy. But the relationship between luminous flux and luminous intensity. Let me talk about how they are related. I've got this sphere here, and imagine this is the sphere that is 1 meter in radius. So from the very interior center, it's 1 meter. And in the interior center, let's say I've got a candle. And let's say that candle is 1 candela. And that's roughly what a candela is the light given off by 1 candle. Now this is giving off, this candle is giving off light in all directions. Now, if this is 1 candela, and if this is 1 meter in radius, and so you take a square meter, so 1 meter by 1 meter, what falls on this square is 1 lumen of illumination. And that's why 1 candela equals 12.57 lumens, because if you were to count how many squares were on this thing, there would be 12.57. There's 12.57 perfect squares around this. And that's actually the surface area for a sphere is 4 pi r squared. And since the radius in this case is just 1, that's why 1 candela equals 4 pi lumens. So going back here, what you do, if you've got luminous intensity, which is in candela, you multiply by 4 pi to get luminous flux, and then you divide by 4 pi to get luminous intensity. And they're all related by this equation right here. E, which is illuminance, that's how much light falls on a flat surface, equals P divided by 4 pi d squared. And d is how far it's from the surface in meters. How far it is in meters. Now there is 2 ways to increase how much light falls on a flat surface, or illuminance. You can A, get a brighter bulb, or B, decrease the distance. And that seems pretty straightforward. Brighter bulb, make it closer. Anybody could tell me that. Now, the inverse square relationship. When you look at this equation, you'll notice that the D is squared at the bottom. And this is called the inverse square relationship. All the light that would be falling on one square right here, if you are, let's say, 1 meter away, if you get twice that away, that same amount that did fall on just 1 square now gets spread to 4. So you got twice as far away, but the amount that's on this square right here is 1/4. That's why it's called inverse square. If you got 3 times as far away, it's 1/9. So you square it, and it's the inverse. So you square this, 3 times 3 is 9, and the inverse 1 over that. It makes sense. It gets dimmer by a factor of 1/9. Lastly, a couple of example problems. What is the illumination on your desktop? If you have a 1750 lumen lamp, so 1750 goes here, because that's lumens, and it's 2.5 meters above, so 4 pi times 2.50 squared. So we can calculate illumination, and that's what it wants to know. What is the illumination? So you just run this through your calculator. 217.50. Remember your parentheses. 4 pi times 2.5 squared. 22.3 lumens per meter squared, or you can say 22.3 lux, L-U-X. And then lastly, example number 2, Wisconsin state law requires that we have 160 lux on our desks. I think I got that equation right. Oh, 4 pi d squared. So 160 goes here. Luminous flux, we're looking for this in this case. 4 pi, and how far above the surface is it? 250 centimeters, or 2.50 meters. And then you solve this for the letter P. And that will tell you how many lumens it takes. Now I'm going to skip over the math doing that just because I'm running out of time. So in summary, illumination, light, blue is really short wavelength, red is really long. There is stuff above and below what we can see, some harmful, some not harmful. Things give off light or they reflect it. Some things allow certain amounts of light to be transmitted more. And there's a relationship between luminous flux, luminous intensity, and illuminance.